Welcome to the video for Lecture 25, Section 1. The previous videos for Lecture 24 showed how to model time-dependent processes using MATLAB. Many well-designed automated process responses have overshoot, which means that the actuator needs to open more than the steady-state setting. For good, underdamped process response, we will say in Section 26 of the course packet that overshoot should not exceed 25% of the final value after the largest expected step change in any input. So if the equipment of a closed-loop process control system is going to respond as modeled, the actuator needs to be sized to provide the expected overshoot. This video goes over the concept of actuator saturation and actuator sizing to avoid actuator saturation, so that actuators installed can provide the overshoot predicted when using underdamped responses. This video will also discuss a couple of safety considerations when selecting actuators. Actuator saturation occurs when the modeled actuator action is expected to provide more input to the process than the device can actually supply. For example, if some electrical input to a fluid heater called for inputting 20 kilowatts, but the power supplied and the relay used can only handle 15 kilowatts, the system would not respond as expected. Or if you have a flow valve that is expected to have a flow of 3 cubic meters per minute at the peak overshoot based on your modeling, and you have installed a flow valve that can only handle 2.4 cubic meters per minute, the real system response will not be as expected or predicted by your dynamic modeling because the valve cannot provide the expected flow. There are at least 3 ways to size an actuator. One method is to base the actuator on the steady-state conditions. For the fluid heater system, the steady-state heat input was calculated to be 828 watts on page 23-1 of the course packet. Would you choose a relay that had a maximum allowed load of 850 watts based on the steady-state value? Another way to size an actuator would be to base a steady-state analysis when the inputs were at their minimum. You were asked to do this for problem set 6, problem 2, when you were asked to find the flow rate of the concentrated material added to the second mixing tank when the inlet concentration of the material was set to 0. For the fluid heating problem, we could size the heat input and relay based on the coldest inlet water temperature and the highest expected set point temperature. A third way to size an actuator would be to base it on the dynamic analysis and look at what the actuator needs to do at the peak overshoot for a well-tuned control system. In section 12, when we talked about block diagrams, it was noted that block diagrams include all the system components, describe the material and signal flows, and could be used to show interrelations between closed-loop feedback control system components. We will use the interrelations capabilities to see the actuator capacity requirements. For the first example, let's see what the heat input needs to be for the fluid heating problem for unit step changes in the set point temperature, TR, and the inlet fluid temperature, TI. Here is the block diagram. Here is the transfer function, Q over TR, for the servo case. The output is the value of Q rather than the heated fluid temperature T. The input for the servo case is the set point temperature TR. The terms on the numerator are the controller transfer function for PI control and the actuator transfer function KV. The denominator terms are 1 plus the product of all the transfer functions around the feedback loop. Here is the transfer function Q over TI for the regulator case. The input for the regulator case is the inlet fluid temperature TI. The numerator in this case is all of the transfer functions beginning at the inlet fluid temperature TI. The denominator is the same as for the servo case. Here are the transfer functions for the servo and regulator cases after substituting in the data for the problem. Here is the heat input needed to respond to a unit step change in the set point for the servo case and a unit step change in the inlet fluid temperature for the regulator case. This is the graph without adding the steady-state heat input value, and we have some negative heat input values which do not make sense. Here's the heat input results after we add the steady-state heat input value of 828 watts. The graph indicates that the heat input and the relay would need to be able to supply around 1080 watts of heat to provide the underdamped response plotted. One thing to point out is that this control model is not tuned. The maximum overshoot is greater than 25%. The next example will have a better tuned response. Key thing to learn from this example is how to find the intermediate values using the block diagram, the process transfer functions, and MATLAB. For the next example, let's use the die mixing problem we've used before. With this example, I'm going to go over the 3 different ways to size actuators mentioned at the beginning of this video. The goal is to see which method is the best. The first method is to size the actuator based on the steady state conditions. Here is the steady state die mixing equation. The amount of die entering via the end control flow plus the die from the die bin equals the amount of die leaving via the outlet flow. Given the steady state data, we can find the steady state die pump flow rate, QMS, to be 0.0007 meters cubed per second. This method has a problem because if the concentrations or flow rates change, then the value of QMS will change also. Another method is to use the steady state equation and set the inlet concentration to 0 or some minimum and redo the calculation. For the data given, the flow rate QM becomes 0.00075 meters cubed per second. The weakness with this method is that the method does not consider the dynamic flow rate that may be needed during some large step change. Here is a graph of the die outlet concentration using MATLAB after the system was adjusted to get good control. Good control, as defined in section 26, is that the maximum overshoot is less than 25% of the final value. For this example, I assume that the maximum set point die concentration was to be 100 parts per million. That meant a step change of 70, going from 30 to 100. This slide shows the steady state die pump flow rate, QM, when we assume that the outlet concentration is 100 parts per million and the inlet concentration is 2 parts per million. The result is a die pump flow rate of 0.00245 meters cubed per second. This would be the pump flow rate after the process has settled down. If we take the pump flow rate at the maximum set point and recognize that the overshoot of a well-tuned process can be 25%, then the pump needs to have a capacity of 25% more, or 0.00306 meters cubed per second in this case. Also on this slide is a graph showing the die pump flow rate QM for the step change of 70 parts per million from 30 to 100 parts per million. You can see that the peak flow rate is slightly over 3 times 10 to the minus 3 meters cubed per second. The graph was generated using the method described earlier in this video for finding intermediate values. The bottom line is that you can get a pretty good estimate of the actuator size needed for a well-tuned process by finding the input needed at the maximum set point value and adding another 25% to that value. The final topic for this video is actuator safety. The question to be posed is, what do you want the actuator to do when there is a power failure? This question is relevant mainly to solenoid valves. Do you want the valve to be open and allow flow when there is a power failure, or do you want the valve to be closed? It may depend, but in many cases, people want the actuator to be closed. When thinking about this, think about flows and impacts both downstream of the actuator and upstream of the actuator. For example, if you close the valve on the outlet of a tank, will the inflow stop too, or will the tank overflow? Here are 3 examples to illustrate some questions for different systems. It takes a clear understanding of the entire process to make an informed decision. This brings me to the end of the video. Write down any questions you have and bring them up in class.